Okay, so good morning to all the present people, to the professors, to the students, to the people of the graduate program in Physics of Maranhão. We have the pleasure to receive the Professor Andrzej Wereszynski. It's okay?
Oh, yeah.
Wereszynski. Professor Andrzej is a very active member of the community of topological defects in the Europe, in Poland, especially in Poland, with a stronger collaboration with the people, with the group of Spain. He is a very known professor, a very known name of the topological defects in the world. So it's a pleasure to receive you in our graduate program, Professor. Thanks very much for your seminar. Thanks very much for attending our invitation. Okay, it's a pleasure. It's really a pleasure for us. And you'll be presented with more details by Professor Fabiano. Okay, so stay with us and a good talk for you and all of us. Okay, thank you.
Thank you.
Fabiano, please.
Okay, thank you. Thank you for accepting our invitation. And Professor Andrzej Wereszynski did master and PhD at the Jagiellonian, I don't know if it's correct. University. Yeah, University, and postdoc at Niels Bohr Institute, Copenhagen, Dinamarca. Andrzej Wereszynski has been a professor at Jagiellonian University Institute of Theoretical Physics in Cracovia, Polônia, since 2002. Several of his papers have appeared in high-impact journals, including Journal of High Energy Physics and Physical Review Letters. He works with topological solitons. Specifically, he is working with schemions and apply them to high energy physics, nuclear physics, and to astrophysics. Together with collaborators from Santiago Compostela, Christopher Adam and Joaquim Sanchez, they discovered that BPS scheme model, which not only solves the binding energy problem of the minimal scheme model, but also gives the leading contribution at high density regime. Together with Christoph Adam, Thomas Romandowiewski, and I don't know if it's right, the name, and Kasia Oles.
This is
Sorry?
It's correct, yeah.
Okay. They discovered the spectral wall phenomenon. He is now collaborating with group at universities in Santiago Compostela, Cambridge, Leeds, and Durham. Attending Professor Andrzej Wereszynski's seminar is a privilege for our program. Thank you again, and Professor Andrzej Wereszynski, you can start.
Thank you very much, and yeah, thank you very much for the invitation and very nice words. It's really a pleasure for me also to present my research for you. And yeah, especially that I know some of you, like Fabiano and Andrzej. So it's yeah, it's also for me an opportunity to have a chance to speak to you. All right, so let's start the seminar. During this talk, I would like to give a kind of a little bit more general overview about the collective coordinate method and its application to solitonic scatterings. Okay? And its work done together in a collaboration with Christoph Adam from Santiago de Compostela, Nick Manton from Cambridge, and my local collaborators, Kasia Oles and Tomasz Romanczuk-Kiewicz, right? So the outline of this talk is the following. At the beginning, my plan is to give really like elementary introduction to the collective coordinate method, okay? I will tell you why it's important, why I think it's worth to construct such models, and then I will tell you how to construct them or how we believe they may be constructed. Right? And then I will give an example of a very successful application of this method for for description of kink-antikink collision in 5-to-4 theory. But yeah, it has been a very long problem how to describe this this collision, this interaction in such a very simple, almost the simplest non-integrable model you can imagine, by means of collective coordinate approximation. And for almost 40 years, it's people didn't know how to do this. So that's a very this result is important because it shows that this method can be applied to really a very huge set of possible processes. Okay. And then I hope I will have a time to present cases where the usual method to build a collective coordinate model fails. Okay, and then you have to enlarge, you have to generalize your approach, and this we call a dynamical vibrational moduli space or dynamical collective coordinate model. Okay, I will be more specific during the talk. So let's start with the collective coordinate method. Okay, good. What's that? What is it? It's the idea is very simple. Dealing with classical field theory means that you deal with infinitely many degrees of freedom. So the collective coordinate approximation means that you reduce your infinitely many degrees of freedom to a finite number. Okay, and the point is that you have to specify this finite degrees of freedom. You have to somehow know which degrees of freedom are important for a specific process and which can be at least at some approximation abandoned. So basically it means that you reduce your field theory, the original field theory, to a classical mechanical system. Instead of field phi, okay, you work with a finite number of degrees of freedom denoted here as xi. Okay, so this is a huge simplification, right? Instead of infinitely many, you have finite number. Typically, it's a very small number. It's like 2-3 degrees of freedom very often. So why it's important? First of all, and this is like my motivation, it's important because it can give an explanation of a specific processes which are observed in kink, in solitonic collisions, for instance, in kink-antikink collision, for instance. Okay, so it gives you a chance to somehow prove, not rigorously, but to find a very good evidence that a specific process or a specific observables are due to some mechanisms which are based on some degrees of freedom, okay, on some underlying degrees of freedom. Then this collective coordinate method also provides you a kind of approximated semi-analytical insight, especially in higher dimensions. If you work with planar solitons or three-dimensional solitons as fermions, then this simplification is very, it's something what you like to have, because scattering time evolution of solitons in higher dimensions, it's a very complicated numerical problem. It's not like in 1+1 dimensions where sometimes this collective coordinate model can be, from numerical point of view, even more complicated in a sense, or more subtle than the original field theory. Then you can treat this model as a something which gives you a test for full numerics in the original field theory, and at least at the end, what is very important, the specification of collective coordinates is crucial for semi-classical quantization of solitons. So if you want to describe, for instance, atomic nuclei as skyrmions, as solitons in 3+1 dimensions, then it's necessary to quantize them, right? Because nuclei are proton, neutron, are quantum particles. So then quantization is essential for the application of such a model. So yeah, you have to quantize them. And semi-classical quantization essentially relies on the collective coordinate, collective motions you specify. Okay. All right. So how to construct such a collective coordinate model? So the construction is very simple. You have to specify a restricted set of configurations, right? So you say that only specific configurations are important for a specific process you want to analyze. Okay? Typically, such configurations are parameterized by parameters which we call moduli. Okay? They are parameters, and those configurations are assumed to be static. Okay? They do not have to be solutions. They might be solutions, but not necessary. But the point is that they should capture the main properties of a solitonic process you analyze. Okay? For instance, a collision kink and kink, or an annihilation of kink and anti-kink. So to specify this restricted set of configurations means that you have to make a kind of educated guess, because it's not, there is no like prescription how to construct this set, right? But once you have it, you plug your configurations into the original Lagrangian, and then you promote all parameters, all your moduli to time-dependent quantities. Okay, and then you integrate everything over the spatial domain, right? Directions. In this case, I consider only one-dimensional objects with 1+1 dimensional field theory, and then you arrive at a system which describes the time dynamics of these moduli, of these parameters. So first observation is that by the construction, you reduce your Lorentz invariant theory into a non-relativistic theory, right? You started with a relativistic field theory, but at the end, your construction gives you non-relativistic ones. Good, that's what you have. And perhaps it can be improved, I hope. But there are two main objects which show up during this construction. One is the metric, which multiplies the kinetic term of your new Lagrangian. And it's really a metric on the space of parameters. It transforms like a metric. And then there is a potential, which is just a non-derivative part of this effective model you arrived on. Good. But as I said, the essential part is to specify the restricted set of these configurations, which you believe are important. Okay? So basically, there is no like well-defined scheme to construct this, to specify this set. There are some hints or some educated guesses which allow us to do this, but yeah, it's a sort of unspecified, not completely specified stage or element of this construction. So there is one case where this moduli or collective coordinate model can be defined in a canonical way. Okay? Once you have static solutions, topological solitons, let's say, static topological solitons, which have exactly the same energy, okay? Then you can imagine that the lowest energy dynamics, the simplest dynamics, happens by changing one energetically equivalent solution into the other, okay? And then the simplest dynamics is just the transition, just the flow between different energetically equivalent solutions. So, like mathematically, it means that you consider only like a kinetic motion, which is related to the excitation of zero mode or zero modes, massless excitations of your solitons, okay? And as a simplest example, I will consider phi-to-4 theory, which is in 1+1 dimension. So we have a real field. Here is the time derivative squared. Here is the spatial derivative squared. So this is the derivative part of the Lagrangian. And then there is potential, which is a double vacuum potential. It has two vacua at 1 and -1, okay? And for this model, there is a single soliton sector, which is populated by a single soliton. So this soliton, for instance, with sign plus, interpolates between the vacuum, the -1 vacuum and +1 vacuum, okay? But because the theory is Poincare invariant, so it has spatial translation symmetry, right? So it doesn't mean, it doesn't matter where you put your soliton. Where is the location of the soliton? It means that the argument of this tangent function can be shifted by any real constant A. Okay, so A corresponds to the position of the soliton, and then you have one modulus which parametrized you a family of energetically equivalent solutions, because due to the translational invariance, all these solutions have exactly the same energy. And then you plug this solution into the original theory, and you derive your effective canonical effective model. But this is a very, very simple model, because the metric, I mean, first of all, it's one-dimensional collective coordinate model, and then the metric is, you can compute it, and it's constant and equals to the mass of the kink, and potential the same, is a constant and equals to the mass of the kink. So this potential is immaterial for the dynamics of this Lagrangian, and of course the dynamics which you can cover by this very simple collective coordinate model is just the constant velocity motion of a kink, right? Because the field equation, which is derived from this Lagrangian, is just a second derivative of A equals 0. So yeah, it's okay, it's fine. It describes a stationary motion of a kink with constant velocity. That's okay, but yeah, it's not too interesting. Okay, so it's too simple. So let's make it more complicated. So the idea is to include not only the zero mode, okay, the lowest energy excitation, but we would like to allow also for more complicated excitation, which, for instance, can be massive excitations, massive normal modes, right? So they correspond to linear perturbation of this kink I consider it. In other words, we allow not only for kinetic degrees of freedom of a kink, but also for internal degrees of freedom. Okay, and it will occur that it's enough to describe really complicated observables or pattern observed in kink-antikink collisions. Of course, now if you include the internal modes, the massive modes, your field configurations you consider, they are not energetically equivalent. For instance, if your amplitude is higher, if your mode is excited with a higher amplitude, then of course it needs more energy. It's a massive mode, right? And again, let's consider this construction for the 5-to-4 theory. Okay, so instead of, now we started with the canonical moduli space, but now we build on top of that vibrational moduli space. We include vibrational modes. So in the case of 5-to-4 theory, the kink has only one internal mode. There is only one mode. It's called shape mode. Okay? This shape mode has this form. It's sinh divided by cos squared. It's again located. The mode, of course, is located on the kink. So yeah, you have this dependence on little a, which is the position of the kink, of the original tang kink. And this mode has its own frequency. And then you have this additional coordinate, capital A, which is the amplitude of the mode. Okay, so you use this restricted set of configurations to construct another collective coordinate model. And then once you plug these configurations into the original Lagrangian, you get this two-dimensional model, right? You have two coordinates now. And the metric is not constant anymore. It depends on the amplitude of the internal mode. Okay, and the potential again also depends on the amplitude of the shape mode. Okay, and what kind of dynamics you can describe using this collective model? It's just a moving, and this is a moving kink. It describes a moving kink which also vibrates. Okay, so this kink, using this model, this collective coordinate model, you can describe a bigger variety of dynamics, but still all the time in one soliton sector, right? It's only one soliton. It doesn't meet anyone, any other partner in the collision. It's just a soliton which moves with velocity a dot and which vibrates. Okay. But of course, it's not too interesting. The most interesting cases are multi-soliton collisions. Okay, and now the question is how to construct this simplified set of solutions or configurations which can capture such collision. Then there are two possibilities. Okay. The simplest one is called frozen vibrational moduli space. It means, okay, that first of all, you have to identify the initial states which take part in the collision. So for instance, in the case of kink-antikink collision, your initial states are kink and antikink. They are separated. Okay, so they are separated enough that they can be treated as a free particles at the beginning. And then the moduli space is defined as a superposition of the moduli spaces of the members of in the collision, right? So you have a moduli space for the free kink, you have a moduli space for the anti-kink, which is free at the beginning, right? So in a sense, I mean, speaking precisely, you have this simplified set of configurations for kink, and you have a simplified, you have the set of configurations for anti-kink, and then you just make a superposition, a knife, you consider a knife sum of these two sets, right? And the point is that your vibrational mode or modes, right, are assumed to have all the time form of the modes as they were on the free solitons. Okay, so they don't, the shape, the form of the modes, the number of the modes doesn't change during the collision. Okay, so let's consider and that's the reason why we call it frozen. The mode structure is frozen from the very beginning. It's decided by the initial states. So let's consider kink-antikink collision in 5-4 theory. Again, 5-4. So you have kink. At the beginning, you have kink and anti-kink separated. So this little a, which denotes the position of the solitons, is a big number. Okay, the solitons are really localized exponentially. So in practice, it doesn't have to be too big number, but let's assume it's a big number. So then you have kink located at -1, and it has its shape mode, okay, and multiplied by the amplitude of this shape mode. And then you have anti-kink located at +a, and it has its own shape mode. And now I consider only a symmetric superposition of this shape mode. So you can consider also anti-symmetric, it's not a problem, okay? So that's the meaning of this frozen vibrational moduli space. Your set of configurations is built out of the sets of the free initial states. And you have to subtract -1 to be sure that asymptotically you are in the vacuum. Okay, so the modes are not deformed by the presence of the other solitons. And it occurs that in many situations, it's a very good approximation. It works perfectly. But there are cases, and I hope I will have a time to talk about these cases also. So another solution, another possibility is that you have to take into account this fact that the modes change during this, the solitons come closer. Okay, and there are two examples. One is the spectral wall, which is related to a transition of a mode, of a massive mode into the continuous spectrum, and it really affects the dynamics of soliton, and you can find this phenomenon only if you consider dynamical vibrational moduli space. So you really follow the change of your mode structure during the collision. Another manifestation of this dynamical necessity of the dynamical vibrational moduli space is the role of unstable solutions, which can change the kink-antikink collision. Okay. So let's turn to the frozen moduli space, which is really a very good approximation in many cases. And let's solve the kink-antikink collision in 5-4 theory. Okay, so what happens in 5-4 theory? It's a non-integrable theory. It means that particles, solitons, can be annihilated, can be created, and when you scatter soliton and anti-soliton, so the initial configuration prepared for your full numerics, which you perform in the full field theory, the initial state is like that. You have kink boosted towards anti-kink. Because it's a Lorentz invariant theory, you have to consider also the gamma factor, of course. And there are two scenarios. One is backscattering of the kink and anti-kink, and they reappear in the final state. As here you have kink and anti-kink, they come closer. Okay, here is the value of the field for x at different time. Okay, so yeah, you have from -1 to 1 and to -1. So we have kink comes closer to the anti-kink. They annihilate for they form -1 vacuum, and then they reappear. They reappear in the finite state. It can happen that they like pass the vacuum twice. So we call they do 2 bounces. They can make 3 bounces, but they can also annihilate to the vacuum. So in the final state, you have just radiation and the vacuum. This plot is taken from a very, very nice review by Goodman and Keridis. Okay, so it's a very nice review about the problem of 5 to 4 of the kink-antikink scattering in 5 to 4 theory. Okay, but actual pattern depends on the initial velocity. Okay, so here I plot the value of the field at the center, which tells you it's like value of the field here at the center, at the origin. And then if it's +1, okay, it means that at the end, for instance, you have kink and anti-kink in the final state, and they travel to infinities. Once you have -1, it means that you create a vacuum, the vacuum, and it means that the solitons annihilated, right? So the if you measure the value of the field at the origin, then you can say what happens actually in your system. So here is the value of the field at the origin at different time. So for instance, here for the velocity 0.3, the solitons, here is +1 in the at the origin. So initially solitons, there is a soliton and anti-soliton. They come closer. They pass through -1 vacuum, and they reappear again, and they are released to infinities. But if you reduce, so it's a 1 bounce big window. But then if your velocity is a bit reduced, then you can observe like 2 bounce windows. So it's the first 2 bounce window, the second, the third, and so on and so on. There are also 3 bounce windows. Okay, then you have again the kink and anti-kink in the final state, but they perform 3 bounces, so they 3 times pass the -1 vacuum. There are also 4 bounce windows, but they are also for certain regions of initial velocity, there are something which we call Bion chimneys, and it's just a region where when the kink and anti-kink decay to the vacuum by an emission of radiation, and they form something which is like basically long-living quasi-oscillon, quasi-breather state, which oscillates and slowly decay by an emission of radiation. This state is called bion, okay, but it's a sort of quasi-breather, let's say. So you see this, the formation, the pattern of the formation of the finite state is very complicated. It depends on the initial velocity, and in fact, it has a fractal or chaotic structure. If you magnify this part, for instance, then you will see exactly the same pattern hidden here, okay, or similar pattern. So yeah. In such a simple model, the final state formation is a very complicated process with fractal structure. So one would like to explain the origin of this phenomenon, why it's like that. So people for many years conjectured that the reason for that is the resonant energy transfer, which means the transfer of the energy between kinetic degrees of freedom, which is just zero excitation of the zero mode of the position of the kink, and internal degrees of freedom, which is the shape mode. So depending on the relative energy which is stored in 1 degree of freedom or in another degrees of freedom, then the kink and anti-kink can be released to infinities, or they will annihilate to the vacuum. Okay, so this is like a game between two partners, little a and capital A, and depending how the energy is distributed, actual situation happens. That was conjecture, and of course you need an evidence, you need a sort of proof that this is the case. And the simplest evidence you can imagine is exactly a collective coordinate model, which is built out of these two coordinates. Little a, which is the kinetic motion, right, the position of the solitons, and capital A, which is the amplitude of the mode. And then you consider this simplified reduced space of field configurations we specified before, right? This is this naive, the most naive frozen vibrational space, and plug it into the Lagrangian, and then you derive your effective theory, your collective coordinate model. But unfortunately, this model fails completely. Well, people for 20 years believed that this model works because there was a typo, some integrals or some metric functions were computed wrongly. There were some mistakes. And then when it was corrected by Herbert Weigel, like more than 10 or 15 years ago, then he realized that this model fails completely. It predicts bounce windows, not at this 0.20, maximally 0.26, but it predicts bounce windows almost at the speed of light. I mean, so you get fractal structure, that's correct, but this the result, the fractal structure had nothing to do with the original structure observed in the full field theory. Okay, so this model failed, and that was a big problem because, people didn't know whether what is the meaning of this of this fact, whether the collective coordinate approximation cannot capture such a violent process as kink-antikink collision, right? That's, we simply didn't know for many years. Okay, but what you can observe studying this original approach by Sujiyama is that there are basically two possible sources of problems. One is the zero vector problem, okay, which means that your metric, this quantity which multiplies the time dependent part of the Lagrangian, the derivative part of the Lagrangian, vanishes at certain points, and then it means that the model breaks down, okay, in a sense. So it's badly defined at this point. So to see this, let's consider our simplified set of our reduced set of configurations. So we have kink, anti-kink again. We have shape mode of one of the kink and shape mode of the anti-kink. And now let's consider the derivative with respect to the capital A. Okay, we need it because the metric, I go back because I have the definition of the metric at the very beginning here. The metric is defined as a spatial integral of the derivative of the field with respect to the parameters, okay? So you need the derivative with respect to the parameters. So let's consider the derivative of the field with respect to the parameter capital A. Then the first part vanishes and you have only this bracket. But then if little a goes to 0, then this term cancels with that term, right? So it means that your derivative vanishes at the point where kink and anti-kink are on top of each other. But then it means that at this point, the metric, because metric is the spatial integral of this, this term multiplied by another derivative, your metric vanishes at this point. It vanishes the capital A component and also capital A little a component. But it means that your dynamical system is not defined at this point, okay? One of these second derivatives is multiplied by 0, and then, yeah, you have no idea. Your system doesn't know how to evolve beyond this point. The important observation is that this approach to 0 of this derivative is linear, okay? It's a linear approach. And then people did some ad hoc regularizations, but yeah, they didn't help too much. They didn't help. So there is also another problem, which is relativistic effects. Okay, look again. This fractal structure occurs for velocities which are quite relativistic. So yeah, maybe relativistic, a kind of relativistic features should be taken into account. Okay, some relativistic effects. Okay, so we have two possible problems which have to be cured or at least understood. Okay, so solution of the problem. First, let's consider the zero vector problem, and it's very easy to solve this problem. You need a new coordinate. Okay, why it's enough? So let's first observe that, how to start? So let's consider just this new coordinate b, which is related to the old coordinate a by this relation, right? Once you replace a as capital B by little a, okay, and you plug it to your restricted set of configurations, then you remember this derivative was linear in A. Okay, this part at little a going to 0 gives you a term which is multiplied by little a. But then, because you have B divided by A, this A cancels with this A, and then it's not 0 anymore. Okay, so yeah, this new coordinate cures the problem, the null vector problem, and that's made in the vicinity of A equals 0. So to have it globally, you have to just replace A by capital B divided by tanh A, because tanh A for A equal going to 0 is A, and for A going to infinity is plus or minus 1, right? So at infinities, when little a goes to infinity, then capital B is just capital A. So you have your usual amplitude of the shape mode. Okay. Why it was possible at all that such a simple regularization? It's enough. It's because the original metric here, although it has 0, okay, so it's a kind of singularity. This singularity is an apparent singularity. If you compute the Ricci scalar curvature, then it's a finite, it's non-zero, a finite number at little a equals 0. At the point where kink and anti-kink are on top of each other, this metric actually it's not singular. This space is not singular. Your coordinates are badly defined at this point, but the scalar, Ricci scalar, which describes you the true property of the metric, is finite. So it means that your coordinate, in a sense, doesn't see the other part of the moduli space. There is another part of the moduli space which is not visible in this coordinate system, right? So in this new coordinate system, where instead of A, capital A, you have capital B divided by tangent A, then you see the other part of your moduli space. And this is the full, then you can plug this restricted set of configurations. You derive your effective collective coordinate model, which is based on two coordinates, little a and capital B, right? And then, yeah, it has Ricci curvature finite non-zero everywhere. So it's fantastic. Yeah, I mean, it could be zero. It's not a problem, right? The curvature could be zero. But it's non-singular everywhere. So the space is completely well-defined for any value of A, any value of B, finite values, of course. And then the potential has this form where these black curves are the equipotential curves. So for instance, this closed curve is a curve which the value of the potential is a little bit smaller than the mass of kink and antikink. This curve here, which extends to infinity, in fact, is a curve with the energy slightly above the mass of the kink plus mass of the antikink. Okay, so it's like, you see, there is one escape direction in this potential. So, and this structure of the potential, together with the structure of the moduli space, those two facts lead to the observed fractal structure. Okay, but once we have the well-defined collective coordinate model, we have to also specify initial conditions for this model. And that's a point where you take into account this relativistic effects. Okay? So initial condition. As an initial state, you have a kink separated with an antikink, right? They are really separated, they are far away from each other, so then you can consider them as independent particles. So from the point of view of your collective coordinate model, your initial configuration is just that, is the kink with zero mode, with the position of the kink, okay, and with the shape mode. This is the initial configuration you should somehow understand in your collective coordinate model. But yeah, we computed this model at the very beginning of my talk, right? We plug it and we derive the effective Lagrangian for this single kink sector with shape mode included, right? So we have metric, we have the effective potential, everything is fine. And then we compute the equations of motion, and they have this form. And the most important observation is that there is a stationary solution. There is a solution which describes the kink with a constant velocity, which means that the little a dot, okay, is constant. I denote it as v. Okay, but when this is constant, to have this equation obeyed, we also have to assume that this all bracket is constant, which means that capital A, the amplitude of the mode, is constant. Okay, so then this is zero. Then the second derivative of the capital A of the mode is also zero, no problem. But then you arrive at the algebraic equation which relates the velocity of the kink, a dot squared, the velocity squared, with the amplitude of the mode. And this is essential. It means that once the velocity, the initial velocity of the kink is not zero, your mode is actually excited. So for the initial configuration, you cannot assume that your mode is not excited from the very beginning, because naively you scatter kink and anti-kink, you don't excite this mode from the very beginning in your full numerics, right? But from the point of view of the effective model, you do like that. Your mode is excited, because of non-zero velocity. So the initial configurations, initial conditions are modified at one point here, okay? And this is essential. Without that, our new effective model fails as well. And in fact, this observation that boosted kink is somehow related to the excitation of the shape mode, it's not surprising, okay? Look, if you take your initial field theory configuration, which is the boosted kink, right? You have this gamma factor. And then you expand in the velocity v. So you have this non-relativistic term, but then you have first relativistic correction. And this first relativistic correction has almost the form of the shape mode. Shape mode is sinh x divided by cos squared x. But here you have x divided by cos squared. If you compute the inner product between this mode, which is called Derrick mode, and the shape mode, they agree in 98%. And also this mode, you can check, it has the frequency very close to the frequency of the shape mode. So in fact, the shape mode somehow is almost identical to the Derrick mode in the case of phi to 4 theory. Okay, so now you have new collective coordinate model, which is well defined for any value of your coordinates, and then you have new initial conditions. Okay? And then you do once again your numerics for the collective coordinate model, and this is the result. Okay. So they agree almost amazingly. If you compare that you have only, if you remember that you have only 2 degrees of freedom in the game. Okay, here is on the left hand side there is the full theory result. On the right hand side there is this collective model result, and there are only 2 degrees of freedom in this model, and the pattern is almost the same. You have 1 bounce window, you have 2 bounce windows. They are more or less in the same position. There is, as you see, a global shift towards higher velocities, okay? And also some of the Bion chimneys at some point form kinks. Kink and anti-kink in some of these Bion chimneys are released to infinities. But this is normal. This is like well-expected phenomenon, because the decay of Bion chimneys is related to the radiation. Okay, once you have Bion, this Bion radiates all the time, and this is the reason why it decays to the vacuum. In the collective model, in this collective model, we do not have radiation. So once you have a Bion, okay, so it will eventually, at the end, it will always decay, but not to the vacuum, but to the kink, free kink and anti-kink, because you don't have radiation. You do not have any other channel where you can transfer your energy. But these are like limitations you are really aware of, and you understand, you understand them very, very well. So fantastic. The frozen vibrational moduli space, the frozen approach to construction of the collective coordinate model works fantastic, yeah, in a very good, with a very good precision, also for kink-antikink collisions, okay? In this case, in 5-to-4 theory. So this is a very good result, very important result for the collective coordinate method. Okay? So the range of application of this method is really huge. There are many processes you can study within this process. But how much time do I have? Sorry, it's so maybe 10 minutes. Can I have 10 minutes more?
Yeah.
Okay.
Yes.
Thank you. So I will go back to my presentation, and now I will talk about the cases where this frozen assumption, frozen construction is not enough. Okay, you have to really take into account the fact that modes can disappear during the collision. Okay, and it's it's related to something which we call spectral walls. Okay, so let's have a closer look on this dynamical vibration moduli space. What does it mean? You take your kink again, okay, but then you take your modes, but you really take into account that the mode have different form as the kink comes closer to another partner of the collision, right? Once little a changes, okay, then this mode function also changes. In fact, it can happen that at some point this mode completely disappeared. For instance, this normal mode enters the continuum spectrum, okay, and becomes quasi-normal mode. Okay. So an example of such theory is 5-to-4 theory modified by an impurity, but it's not like necessary to consider impurity. You can consider kink two scalar fields in 1+1 dimensions, okay, and then you can also find this phenomenon. But this kink impurity model is the simplest setup, and it's simply from the ideological point of view, and also numerically is very clear. So let's consider this impurity deformed 5-to-4 model. Okay, so then you can also find the kink sector, single kink sector, which is again a BPS sector. It means that there are like infinitely many solutions of this equation, okay? Because usually if you add an impurity to your scalar field theory, then your kink, your soliton, interacts, I mean, is attracted or repelled by the impurity. But if you couple an impurity in such a way, then your kink statically doesn't interact with this impurity. It means that again, you can construct canonical moduli space, okay? So you have infinitely many energetically equivalent solutions which describe a kink at any position with respect to the impurity, okay? So your kink, in this case, it's anti-kink. You have anti-kink. At x at the origin you have impurity, so the profile is a bit deformed, and then it goes to -1. Okay, to -1. So it's basically anti-kink. Okay, and then this anti-kink can be located at any positions with respect to the origin where the impurity is located, and all these configurations, all these curves correspond to the solution which has exactly the same energy. Okay, so this is the case with this parameter alpha equals -1. Here's a parameter, okay, and +1, but it's immaterial. So the point is that even in the presence of this impurity, you have infinitely many energetically equivalent solutions, so we can construct canonical moduli space. Okay? But although the energy of the solution is not changed by the position, by the distance between the kink, the anti-kink, and the impurity, the mode structure changes. Okay, if your impurity is strong enough, then at some point, if this distance, it's called here x0, but it's basically this little a I have here, which yeah, we had before, which is just a position of the soliton. So if the soliton is far away from the impurity, you have just phi to the 4 theory, okay, and you have free kink or anti-kink in phi to 4 theory, and you have one mode, this shape mode with the frequency square root of 3. But once the anti-kink comes closer to the impurity, the mode changes. Okay, all these solutions are static solutions, so you can make a linear perturbation at each little a, and then you find the mode structure, and you can find that at some point the mode hits the mass threshold, and there is no normal mode anymore. So beyond this point, there is no normal mode. Okay. Yeah. And this point can be only detected if you consider the dynamical vibrational moduli space, if you consider that the mode structure really changes during the collision. If you consider the frozen vibrational moduli space, then your mode, the frequency of your mode will be always square root of 3. Okay, nothing changes. Or at least the mode will be all the time there. Okay. So, yeah, on the level of the collective coordinate model, it means that your moduli space metric, okay, will have essential singularity at this point where the mode enters the continuum spectrum, when the mode disappears. So your model, your collective coordinate model, will break down at this point. And this is essential singularity. It cannot be cured by change of coordinates or something like that. But nonetheless, it's important point because it's not like it's not like the fact that your model failed and yeah, that's wrong description. Not. This point is has a physical meaning. It corresponds to a physical observable phenomenon. Okay, so the breakdown of the dynamical vibrational moduli space gives you an important information. So this is this spectral wall. So I have to explain this plot, and it's the position of the anti-kink, okay, with respect to the impurity, okay, and it's just the position. So this is just this little a, let's say. This is the little a. So at the beginning, it's you see there's a constant velocity motion of the initial anti-kink, and then this the right plot is let's focus on the right plot. Okay, so depending on the initial on the amplitude of the mode you excite initially, there are different behaviors. If you do not excite this amplitude at all, okay, so it's this almost yellow colors, then your soliton passes the impurity almost unaffected. Okay, if this mode is 0 excited, then you really pass it almost yeah, without any distortion. But once you excite this mode initially, then you meet kind of critical value at which your kink, or anti-kink in this case, is forms almost forms a long living state bounded on a certain point, on a certain at a certain distance from the impurity. Okay, and this distance where this long living stationary point is formed is exactly the point where the mode enters the continuum spectrum. This mode you excited. Okay, and if you excite this mode even more above this critical amplitude, then you will be reflected by this point. Okay, at this point. So we call this point as a spectral wall because it's a wall met during evolution of a kink, and spectral because it's due to the spectral flow of your mode structure, okay, of the flow of the mode structure. And at this point, really your collective coordinate model breaks down. But at least this breaking, this singularity of the moduli space allows you to detect, to specify these spectral walls. So you see, it's this numerical simulation is performed in the full field theory. So this is the real effect felt by SOLITON, and it can be explained only within this dynamical vibrational moduli space. Within the usual frozen vibrational moduli space, you cannot see these spectral walls at all. Okay? And the last example where you can meet, you have to consider this dynamical construction is the case with unstable solutions. In this case, it's spharelon. So again, it's not necessary. It can be, you can meet this situation in many other setups, but the simplest setup perhaps is again slightly modified phi to the 4 model. It's a phi to the 4 model with a kind of another impurity, but it's not really essential how this model looks like. But what is essential is that you still have a kink and anti-kink as a free initial states, but there is also an unstable solution with a finite energy. Such an unstable solution with a finite energy is called spharelon. Okay, and it's very important object even in a standard model where people still search for it in LHC, for instance. All right, so in this model, the spharelon looks like that. Okay, depending on this little epsilon, it's a parameter of this model, the spharelon looks differently. Yeah, in each model, for each epsilon, this spharelon looks differently. So it's a solution which goes from -1. It has a bump and it goes to -1 again. Okay, but this spharelon is an unstable solution, so it has a negative frequency. I mean, imaginary frequency, but it also has its own normal modes. But yeah, of course, it's unstable. So once you perturb it, it will decay. So now, what you can do, you can scatter kink and anti-kink is in such a model. Okay, so you prepare your initial configurations, which are exactly as all the time during this talk. And what you find, for instance, for this epsilon squared equals 0.2, you find a fractal structure again. It's a very subtle fractal structure because it's, you see, it's a very narrow, almost non-relativistic for non-relativistic velocities, but there are 2 bounce windows and there is big 1 bounce window. Okay, so you would like to know what is the origin of this fractal structure in this case. So this is another plot which corresponds to the former one, where I plot the position of the soliton, of the incoming soliton, for instance. Okay. Yeah, we do not excite any mode at the beginning. So the soliton comes. Okay. It passes. It goes. As you see, I plot only the the value of the field at 0 and with respect in time, right? So for instance, for different velocities, it means that we are at different points in this fractal picture. Okay, and then you see that you can form a kind of long-living state, okay, where you have some oscillations, and the position of this state, of this stationary solution, it's is exactly related to the spharelon, okay, because the position of the spharelon also defines you the value of the field at the origin, okay? Or in other words, the value of the field at the origin can suggest that you are dealing with the spharelon. And here is exactly the value of the field for the spharelon solution. So you see that your kink and anti-kink forms a sort of quasi-periodic state, which is exactly located on the spharelon. And the frequency observed here is the frequency of the spharelon, one of the positive frequencies of the spharelon. So in other words, this fractal structure is not due to the shape, the original shape modes of the free kink and anti-kink, but it is due to the mode structure of one of the mode located on the unstable solution, which is this spharelon. So of course, this fact can never be detected if you start with the frozen vibrational moduli space. Okay, you have to really somehow know what happens with your fields and with the structure of your modes during the collision. Okay, so let's summarize. So yeah, the summary. In the summary, I just want to say that the collective coordinate model method is really powerful. It works perfectly for BPS models in higher dimensions, like vortex, anti-vortex, or vortex-vortex in vortex, multi-vortex configuration dynamics in Abelian-Higgs model at the critical coupling. Yeah, it works perfectly even for a kink-antikink collision, like in 5-to-4 theory. But in this case, it's always important to remove apparent singularities and to really understand some relativistic corrections. This is crucial, this relativistic corrections, because the collective coordinate model somehow provides you only non-relativistic limit. But this frozen vibrational moduli space sometimes requires an extension, and this extension is provided by this dynamical approach, and then you can explain spectral walls, and you can really explain fractal structures which are not due to the initial configurations, but due to some unstable solutions like spharelons. They can be other possibilities also. Okay, thank you very much. That's all.